Swayam Prabha. Digital India. Educated India.
What we are going to talk about is almost end-to-end compiler and we may touch upon different parts of the compiler. We will actually look at one. I may not be able to cover all the aspects of whatever the compilers that I worked on, but I will definitely touch upon some of the aspects of those, because some things I have in fact worked long back and I don't have all the material for that, and I couldn't find it also on the web. I had to create that. So what I have done is that I tried to in fact avoid too heavy terminologies here. I tried to avoid ADA and the other compilers that I have worked on. So first compiler, that actually a translator that I worked on, was a C language to one particular language, which actually I don't know whether it is still being used, but it was used for telecommunication. It was invented, or it was discovered for the telecommunication type of writing a programs for writing a programs for this telecom exchanges and all this thing. That's the language is called as a CHILL, CHILL. Okay, and this particular it's because of some acronym, is because of certain basically committee and certain, it's a I think CCIT or something like that. There is a communication worldwide communication technology group, so which has named that, coined that word CHILL. So I worked on that C to CHILL translator. It's not a compiler. Now you can see that one source language to another source language. Why? Because CHILL becoming a standard, my parent organization wanted that, okay, existing C programs, we need to now move to this particular language. At least we should understand that, okay, we are actually all these exchanges and all this thing, telephone exchanges and all, there is a heavy parallelism, heavy concurrency required, and the way it was achieved was with the help of obviously OS calls and all this thing in case of C. Now moving forward, basically they wanted to in fact have a better control over this concurrency usage and other things, so they wanted to move this to CHILL. So that's the one part I worked. Then I worked on a CHILL compiler and then the ADA compiler. So those all, ADA is very much used, so I will cover some of the aspects of what are the different parts of that particular ADA compiler, or what it teaches you and how it differs from the typical kind of whatever the phases we discuss in particular books, popular books like a dragon book or tiger book or whatever that you are referring to. Okay, so before we get into those things, let's touch upon some of the basic concepts. Now we know that there is a compilers, and there are nowadays interpreters are quite popular, maybe because they were earlier also they were popular, but they were mostly used for the scripting language. Nowadays they have become a mainstream with the Java and C# and all this thing, but there is a difference actually that this particular type of language interpret. So compiler, we know that, okay, there is a source program given, then we generate a target program. Obviously I am missing some of the things I have not mentioned here, that there may be a sometimes compiler will generate assembly code, assembler may convert assembly code to machine language, and then maybe a linker which is involved in. So you have heard of this assembler, linker and all this thing, right? You must have learned about it. So it may basically combine to create a executable. Now this is a simple way of understanding that a compiler, it takes a source program and generates a target program. There is an input, and the target program is obviously your target program, which takes certain input and generates output. So compiler actually instead of target program, as I mentioned, sometimes it may generate incomplete machine language. Okay, why incomplete? Why incomplete? What is basically what is missing in that? So basic thing that is missing is that you are actually compiling in parts. Okay, you are compiling one particular file, maybe in your case, or it may be a module, and that module refers to another module, and you may have actually a static linking may have to be done. In case of Java and all, it's basically you are referring to certain packages which gets resolved at the compile time and gets loaded as per the class path at the runtime. Okay, so there may be a slight difference here, but this is still C kind of language where you generate a machine code, okay, or even C++. Most of the time you don't generate a virtual machine code. Yeah, and also for the embedded programs you are generally do create a executable. This is the path that is followed. In the interpreters, obviously you have a if it is a pure interpreter kind of language, that is the first one, where the interpreter actually does not generate a virtual machine code, but it interprets and then generates the output. For example, take an example of maybe there is an internal representation of your program like a Perl kind of language, okay, or awk, I don't know whether you heard of it, awk kind of language. Okay, what they do, they actually given the program, it acts as a machine by itself, okay, and it interprets it and generates the output. Your program actually, whatever the program written, that is interpreted and you generate the output. Whereas in the case of Java, you generate a virtual machine code, okay, and that is a byte code, that is the virtual machine code, or we can say byte code here. It generates the byte code which actually is a part of that virtual machine description of Java JVM, and that particular now the thing is that this virtual machine actually, in fact that virtual machine provided by Java, that is Java itself, that is called as, that actually interprets that particular Java byte code, and that actually as it interprets, obviously your program gets executed and you have input to output, correct? Is it clear? It is a very simple. So let us look at the now in a more holistic way, that what are the compiler phases, and you have learned some of them and you have gone deeper into some of the aspects actually, but let us try to again look at take a full view of this compiler as a system basically. So we will be in fact revisiting that again and again, but the thing is that there are certain differences that happen whenever the commercial compilers are created. So I will talk about that at the end actually, that how this particular things change basically. So obviously that we understand that there is a front end analysis that is done, that is you have a source code. Somebody mentioned, I omitted that preprocessor, but yes, you do a lexical analysis, and then there is a scanner which does the lexical analysis. There is a parser where you do the syntax analysis. There are lots of activities happen during this particular part. During the syntax analysis, you may create a very important data structure in a compiler which is called as a symbol table. You create also abstract syntax tree, okay, which gets annotated with the semantic analysis, okay. We will see that how it gets represented and all, we will see the brief about it. This particular semantic representation, this particular semantically represented actually abstract syntax tree is different from the parse tree basically. So many times, many of this particular intermediate representations, there are two parts. One is that this particular abstract syntax tree, and there is another intermediate, there may be three intermediate representations in the many of this compiler. There is another intermediate representation which actually allows you to do a better optimization, and the third intermediate representation which is closer to the machine, which actually allows you to do a machine level kind of optimization. Okay, so there is a RTL register transfer language which is common actually for this particular kind of work. We will see that there are some of the typical kind of GNU kind of compilers. They have something very good compilers. In fact, GNU GCC compiler is one of the good ones. There are earlier attempts also being made, like a portable C compiler and all, where this semantic representation actually is they call it as a generic, actually they call it as a generic representation, and there is whenever you actually move it to the what they call it, the 3 address code or 2 address code, 3 address code, sorry, that's basically they call it as a GIMPL. Okay, we will see that part actually how this gets generated. So now this is a flow, and there is you can see at the bottom there is a very important symbol table that is there, and also abstract syntax tree. Okay, now tell me here one thing, how at a time the compiler is actually compiling only one file. Okay, your one file is compiled. How basically it differs from the language to language, but how in a language like Java, the references are preserved, and how basically the compilation of the other module which is referencing to the earlier compiled module is actually resolved. Java or C++, any of this, some of you are familiar with Java. Do you know that how I have two particular files, one contain let us say a class ABC and another contains a DEF. ABC refers to DEF, okay, ABC refers to DEF. So how the compilation order takes place, what is the compilation order generally, and how this particular at the if the sorry, go ahead, answer. Anyone wants to answer? What is the compilation order? ABC is referring to DEF. So what is the compilation of order? Obviously DEF has to be compiled first and then the ABC. But while compiling ABC, what I need to specify, I just need to specify that okay, there is somewhere a DEF available in the class path, correct? That is the way you specify. And what happens if the DEF is changed afterwards? So let us consider multiple scenarios, okay, multiple scenarios. One is that you may have to, you can just change the implementation of DEF, still that particular, just compiling DEF will still work in the case of Java or not. Will it work or no? It will work, right? So this is the very simple scenarios you can think about it. But some of the languages like Ada, they require a typical kind of library managers, okay. It may be a actual library manager which in fact reduces the overall compilation time, because there is no dynamic, it is not at the execution time, there is no basically a virtual machine which is interpreting your program, there is actually the machine which is in fact the hardware which is executing your program, and you need to give a executable code, and you need to be also smarter in compiling the overall basically because there is a millions lines of codes. It is not generally the languages like Ada are used in this avionics and all this software. There basically there is a million lines of code, and you change one thing, you have to ensure that okay, the overall basically the compilation time is lesser, and also it is a smarter compilation that you do it, and at the same time I should be able to create the executable faster. So there is all these references and all these things are maintained in a something called as the library managers in these languages, okay. So there is no dynamically that okay, I invoke that ABC and then at that time whatever is compiled DEF I will use. That is not the only thing that can happen in case of this fully compiled languages and not running through the VMs, okay. So there are multiple things that we have to do, we will discuss that, but let us look at the simple flow that okay, we have seen that okay, compiler the system, there is a definitely there is a lexical analysis, syntax analysis, semantic analysis, we have seen that. Let us see a simple example that how it looks like, okay. So we have omitted this preprocessor and other things basically. So what happens is that there is a source program given, okay. Let us consider our own language where there is a simple thing that is given here, function sum, which is actually there is a return, it is returning that n star n plus 1 by 2, okay, and that is n is a parameter, and that is a function we are defining this function, correct. This is the function that is defined, and here what happens is that the first thing you do, as somebody mentioned, you do a lexical analysis. So what are the technologies and what are the basically basics that you need to use there? Definitely there is a, when I need to tokenize that, just check that, so right, I need to tokenize that, and that tokenization will allow me to do a better basically. So many things that you have learned as a technologies and the concepts and all whatever you have learned. So for example, you have learned about regular grammar, regular expressions, and obviously that actually is the first step, that is the first set of concepts that help you to understand and do the better lexical analysis, so tokenization. So there is a deterministic finite automata, obviously regular grammars and deterministic finite automata, they go hand in hand, and you are representing that particular overall lexical analysis step using this regular expressions and the patterns and all this thing. You use a lex or maybe a flex, or there are many other generators, okay, lexical analysis generator these are called, okay, that exists. You can use them and you can write these patterns and you can specify that okay, A to Z, capital A to Z, 0 to 9 etc is a word, sorry, is an identifier, correct. You identify all these tokens, correct. So this is what is shown here, that there is a func which is a ID, which has been recognized, some as a ID which is recognized, then you tokenize this particular input. Is that fine up to this point? So you have tokenized this. Now after you tokenize this, so you tokenize this, and this is a basically first step you have done, right? Second step, second phase or step or whatever you can say, yes, some of the things may happen in parallel, by the way. Syntax analysis, lexicon analysis, it need not be a complete pass by itself. It need not be a complete pass by itself that you create all the tokens and then you do the syntax analysis. That is not the always happens. What happens is that generally you do the lexicon analysis, while doing that there is also syntax analysis happens, okay, of that whatever the tokens. So in fact parser is driving the lexer, parser is driving the lexer, and that is the way it happens generally, okay. But though we are showing it here this way, it may happen that parser is driving. So it is always, many times there is a syntax directed translation, that is a word, that is a phrase that is used, and that syntax directed translation is actually nothing but at the center of this overall, as a driver for this overall compiler, is a parser, okay, is a parser which actually is driving this overall compilation process. That is a syntax directed translation, you might have heard about it. So let us, but that is okay, but let us consider this one phase by phase approach and pass by pass approach. So we have tokens. Now there is obviously, you need to understand whether it fits into that grammar of that particular language. So there is a, obviously you represent that language grammar, context free grammar, and you represent it using the Backus-Naur form many times, okay. And that particular grammar, so there are concepts that are used for this parsing, is that many of this particular context free grammar you need to understand. You need to understand whether it is a, this particular grammar is can be recognized through the parsing, L2L parsing, or it is a, you can do it with LALR kind of parsers like a YAC. YAC is a LALR, right? So what is the LALR long form, by the way? Look ahead, left to right. So it is a type of LR actually, okay, and that is the way it is. So so there are lots of other concepts that has in fact evolved, and which made this syntax analysis much basically complete through this concepts of this. You must have heard that, okay, there is a language hierarchy and this automata and all this thing, okay. So they go hand in hand. So there is a push down automata, okay, that is basically what is used here, and there are lots of basically parser generators like YAG, Bison and Java CC. Lot of them are popular, some of them are LL, some of them are LALR, some of them are LRK kind of, there are lots of them are available actually, okay. So what happens here, syntax analysis when it is done, actually this is not a syntax tree, this is not a parse tree, this is not a parse tree. Now if you look at actually speaking, this is a more of a hodgepodge between parse tree and abstract syntax tree. I will show you the what is a parse tree means later. So syntax analysis actually in fact what it does is actually it parses the overall tokens, right, it parses this and it generates the parse tree, what we can say, okay. This parse tree is it has lots of basically syntax specific kind of unnecessary information and structure, which is not important actually many times, okay. So what we need to do is that we need to represent that as a abstract syntax tree, okay, which may not have a complete information still, but it actually represents the program. So for example here the sum, there is a parameter n and there is a body which is actually representing this particular divide, there is a divide, okay, there is a divide operation, and you can see that there is again a multiplication operation and there is a n here, and then you can see that this parenthesis actually is removed here, but you are representing that because of parenthesis you are representing n plus 1 here, and then you are multiplying that with n, and then the whole thing is divided by 2. That is basically the way the all these rules of precedence and overall basically association etc. are taken care, and you have removed all those details about how actually the parsing has taken place, what is. So I have not specified here the grammar, I am assuming that okay we have somewhere the grammar for this particular language, but that is basically precedence and all this thing that and association that exists, and that is the reason this is being represented like this, okay. So good, so far so good. Now moving ahead, I need to do a semantic analysis. I need to do semantic analysis. So semantic analysis, it may happen as it may happen as we are doing a syntax analysis, but some of the parts of the semantic analysis may need to be done as a separate pass after the full syntax analysis is completed. Okay, sometimes it may have to be done. Now what I need to do? I need to do a semantic analysis here. So semantic analysis, obviously I have to do a reference resolution. So you have seen that earlier slide that I have already started building my symbol table, correct? But that symbol table does not have complete information, may not have complete information. I need to now add to that actually that okay, n is integer, fine, perfectly fine. Now n is definitely we will get a certain things through the lexical scoping. Have you heard of the word lexical scoping? Okay, so let us consider that particular, what is the concept of lexical scoping. So you are writing a program, and when you write a program, what happens is there are parameters, then there are local variables, there are static variables. Okay, so they are actually according to the syntax you are representing them, there is a position of them and all this thing, right? So that actually here I can make out here when I am doing the syntax analysis itself that this is a parameter. Okay, so there is a, and then this particular, obviously n will be applicable up to this closing of this particular function. Okay, so there is a lexical scope that has been defined. Okay, and that is basically a function, and it is statically known that okay, the fact that okay, this is visible to me. Okay, that's a, so some of the things are available to you, but you definitely you need to do a reference resolution. For example, in the syntax analysis, you don't know that this particular n, this particular n is the same n. This particular n is not the same n, is not known to you where it creates a problem. Okay, fine, okay, I will do that. Last time I used it actually, but anyway, that's fine, I will do that. So sometimes, okay, I will remove them, this particular pointer. Can you see the cursor? I can see, now it is there. Okay, sorry. So this particular n is actually referring to this n, is all this information, that is the reference resolution, type checking whether this particular star is which type of operation this particular star is. Can you just close that? What type of multiplication operator is this, then what is basically plus, all these things happens during the semantic analysis. Okay, semantic analysis also will check all this, obviously operator overloading will be there, all those aspects has to be taken care. Okay, now here, so what will happen is that it is mentioning here that this is the int operation. So what is the basic thing that the semantic analysis do is bring to the surface semantics of the program so that you can do a correct translation, you can do a correct interpretation as actually expected and as directed by the language. Language has certain rules, language has certain semantics rule, and according to that whether you are using all these things or not. If you have written the algorithm correct or not, that is not semantic analysis worries, obviously they cannot do that. But what is there, that is where you use that axiomatic semantics and operational semantics and all this thing, program correctness. That's your part of it. That's not a semantic analysis, right? This is semantic analysis actually brings to the surface semantics of the program, that what this program actually is means in this particular language, that is the plus means here it is the integer plus, or whether it is a multiplication, or it is a or it is a real plus, or it is a something else. So it basically brings to the surface meaning of that particular different maybe the operators, different usage of that particular features of that language, etc. Okay. Along with that, it also makes this n more specific. Okay, that means n now will contain, this particular n is an integer, that information will be recorded. Sometimes it may this particular n in the abstract syntax tree, it will refer to this n, obviously it will be, it should have been referring already, but it will correct that if it is something else was missing there. Then this, so these are the things that happens actually at this stage. Okay, right. So who checks whether the particular variable, suppose n is used here, okay, but it is not defined, where these things are checked? Correct, that is a symbol table, but whose responsibility it is to say that okay, the particular variable is not defined, whether it is a syntax analysis or a semantic analysis? Semantic analysis. So what happens is that, as she mentioned, that it is not defined in a symbol table, so it is a syntax directed approach that we take. That is why actually it gets mixed between syntax analysis and the semantic analysis, but actually it is a semantic analysis. You are saying that okay, a particular variable that is used here is defined or not. I find out that during the semantic analysis. So all these things actually, so you bring out the semantics and resolve the ambiguity. If there is a plus that is there, whether what type of plus, all these things you will resolve it. So is this clear up to this point? Simple? Okay. Now let us move ahead. Now what happens after that? After that you need to generate either the virtual machine, Java bytecode kind of bytecode, virtual machine code, or you have to do a machine code. But the thing is that many times we find that there are lots of basically maybe a redundant code exists. There are some of the things basically you can optimize better, okay, you can do it much better, because the programmer has to write it in a simple way, and it is a responsibility of the compiler to ensure that okay, you give a better optimized code. Programmer should use a good algorithms, definitely he should write in a good way, but there is a limitation because he obviously wants a program to be readable, okay. He does not want that particular to be too cryptic, so he may not introduce too many temporaries. He may refer a plus b many places, okay, as a plus b itself. He may not say that okay, t becomes a plus b and I use t, so he may not optimize that part, okay. So I need to basically do the hoisting of this particular common expression elimination and all these things that I need to do that, okay. It may happen that sometimes he may initialize a variable and he will still use, he will call maybe, or he may use basically ai, whereas I actually is that I is a 1 here, okay, but he may say ai. So I may like to do a constant propagation here, okay. I may do a definition and usage analysis, def-use analysis, that is commonly called, so that I can actually make it a much optimized kind of thing at the minor level and not at the major level. You need to have the program, obviously you need to write a good algorithms and you need to write a good programs, but this is a basically still you will require optimization, okay. So what optimizations are done? Sometimes the optimizations are done on the directly on the tree, that is a annotated AST, but many times what they do is that they generate an intermediate representation, which is a what is called a 3 address code. That 3 address code evolved because the machine instructions are 3 address codes most of the time, okay. How many of you know assembly language? How many of you have learned assembly language? You, all of you have learned? Okay, tell me some instructions for arithmetic instruction. Can you just tell me a few arithmetic instruction? Sorry? Add ax, add ax bx. So you are in 16 bit still. Okay, fine, good. What else? Add. What are the other instructions? Okay, what are the other instructions that you have learned? Jump and all these things. So some of them are single operand, some of them are, but generally the instructions, actually there are multiple computers nowadays, as SIMD and all this thing architecture. So architecture that we are actually, I mean the traditionally being used actually, and still it exists basically, they are nearer to this particular kind of 3 address code, and that is why you generate intermediate representation as a 3 address code. But the thing is that there are many, obviously there are many other machines actually and many other computers where the architectures where this particular kind of intermediate representation is not good. We will not touch upon that, but there are multiple, and there are there for last 20 years. Many of these supercomputers, many of these data flow machines and all these things, they require a different representation. We will touch upon something which is like your JVMs or your Intel kind of microprocessors or MIPS processors, etc., where this particular code, this particular intermediate representation really makes sense. So what we are doing here, the annotated AST we are converting it to 3 address code, where we are saying now T1, so we start from the bottom, see this now how the order, now the order becomes important, correct. Now this order, actually very interesting part is that this order may be also defined by the language, order may be defined by the language. Sometimes it may, so for example your and or operator, you need to have the left hand side evaluated when you are using the shortcut and, correct, am I right? All of you are familiar, right? They all of so left hand side should be evaluated first and then right hand side. This order is defined. Similarly, for the even for the plus and commutative operators and associative operators, some languages say that you need to evaluate first left hand side and then the right hand side. Why? Because if there is an exception occurs in the left hand side, the right hand side does not proceed basically, obviously, correct. So here order is defined here, so T1 becomes n plus 1, then T2 is equal to n star T1, T3 is T2 by 2. So and then ultimately you are assigning to ID1, which is the return value, which is you are assigning T3 here. Is it clear here up to this point? Is it simple, clear? So far so good, right? Symbol table will be updated at this stage. At this stage it should be done just before that. This is a very good question, I should have written there. So before this particular, after semantic analysis and before the intermediate code generation, yes, symbol table need to be updated. Why and for what? Not really, okay, maybe yes and no. I will not really put all the temporary variables in this symbol table. What else? Which type of value it is holding, okay, what else? Intermediate code generally is independent, but what she said is right. Will symbol table will be updated? Yes, it has to be updated, in fact before this intermediate code generation, and many times. Why? Because what happens is that you need to do a, so there are multiple approaches, sometimes it is done at the semantic analysis time, sometimes it is done afterwards, okay. But just to as you have highlighted the point, I am just taking this here, that what happens is that the n is a parameter, let us say. So there may be a local variables I, j, k, l, m, n, o, p, okay. Let us take a, so there is a storage required for all of them, okay. And there is a, so what happens is that, or there may be a your record is there, right. That record actually what do you call as a class actually, and record, or maybe it is a, it's called multiple things actually, but you understood, right. That's a struct and a record and the class that contains the fields. So these fields themselves may have certain offset within that record. So suppose there is a record or the structure which has integer I and integer j. So the first integer I is at the 0th offset of that record, whereas second integer j is at the offset after the one word, correct. So this particular storage assignment or the binding of the variables may be done immediately after semantic analysis, but sometimes it may be done afterwards also, okay. So during the doing this before, sometimes it helps, because if you are referring to the offset with respect to that pointer of that, let us say a structure or any other thing, it becomes easier for better optimizations and all this thing, okay. But there is a challenge in doing always before, so we will talk about that, okay. So what happens in the afterwards? Afterwards you do the data flow, live line analysis, loop optimizations and all these things, agreed? Perfect, okay. And obviously there is a very simple optimization done here, that instead of, so T3 variable temporary is not required, and it may be, so all this T1, T2 etc. now requires in fact a space. Somebody was mentioning adding it to symbol table, T1, T2 all of them require a space. Maybe it is a register sometimes, or maybe it is a temporary variable in a, so AX, BX as you are mentioning, maybe it is a register, or maybe it is a some temporary variable allocated on a stack, correct, right. So that space, that register allocation and all this thing, that happens during this code generation, okay. And you do the, there are many concepts and many basically formal approaches, that graph coloring, maximal Munch approach for pattern matching etc. of this particular thing is actually happens at this stage. Okay, to select, so there is a pattern matching here also, remember that there is a pattern matching here also. So pattern matching for the proper instruction to be selected. Okay, so this is the flow. Up to this point it's fine, got it? So complete, we have done complete compiler view, actually we have seen it. Is it clear? Any question? Very simple cases we have considered. Let's repeat this to some extent and now explode to some of the things. For example, we have not covered a parse tree. I have not mentioned what is the difference between parse tree and this one. So you can see that whenever I have the expression like this, whenever I have the grammar like this, expression is expression plus term, expression minus term, term like this. Okay, the parse tree will look like, for this particular kind of expression it will look like this. Okay, expression, you can see that there is a minus here. Okay, and then after that there is obviously all this precedence and all this thing, you see that depending on the basic how this particular grammar is written, it may change. So this is basically a parse tree here. This parse tree has a lots of basically intermediate information and the intermediate basically structure, which actually now need to be, in fact we are not interested after doing after we have done the parsing, we are not interested in all these things, right? And that's why there is a syntax, abstract syntax tree. So abstract syntax, you have abstracted out that particular syntax tree, correct? You have abstracted out that syntax, you have basically, that's why it is called as abstract syntax tree. So generally this parse tree to abstract syntax tree, it's sometimes it's difficult, sometimes it's easy depending on your grammar of the language and the way it is written. Okay, so this is the abstract syntax tree generated from generated while doing the syntax analysis. I will say while, or created while doing the syntax analysis, right? Got it? So you are doing the parsing, and while doing that you generate this syntax tree, abstract syntax tree. Now this needs to be annotated as you do the again we are now slightly elaborating more on the how this particular information gets added. If I do a semantic analysis and I also specify the what is the storage that will be occupied, that you were asking that question, that you can see here that semantic analysis and also I have done the certain other annotations of what basically the space it occupies, storage it occupies. So it is mentioned here B is SP plus 16. I will explain about that more later, but have you done the storage allocation and all? No, okay. So this is basically some of the things that will get specified, actually not always during semantic analysis, but yes, there is a, we can say a binding is done and you also allocate the storage for those basically variables, that you are done it here, and so that's why all this information gets actually goes into the symbol table, and you are referring, B is referring to that symbol table information, but it is shown here on the annotated syntax tree, because abstract syntax tree, because it becomes easier for you to understand. That's the reason it is shown here. Okay. So this is the annotated abstract syntax tree where all this information is available when so I can walk through that annotated abstract syntax tree, and I should be able to generate in fact code also if required at a later stage. Okay, and that's what in fact you are doing. So let's look at the semantic analysis again, because that annotated syntax tree that I have shown earlier, abstract syntax tree I have shown earlier, I have not actually done the I have not carried out certain steps that I should have done it as a part of the abstract syntax semantic analysis. I need to, or maybe it's a sometimes it's done along with semantic analysis but done at a later stage, but still I want to specify more about this particular semantic analysis as a more enclosing kind of approach, where we are looking at that, okay, we have said that we have resolved this particular what is the operator means here. Okay, what is basically a type of the operator, I have resolved that in the semantic analysis. Do I need to do the implicit conversions? yes, I may need to do it. So I can in fact expand the tree sometimes. So annotated abstract syntax tree, you may have to expand it. So for example, you may be using a generics, you may be using a overloaded operators. All these things may require a certain kind of conversions, implicit conversions, or there may be explicit conversion given, and that explicit conversion you may have to translate it to the maybe internal calls of the library calls that convert integer to float, convert integer to string. Okay. So all those things basically may happen during the semantic analysis also, but actually it is a optimization done, though it is not always a semantic analysis is not supposed to always do the certain conversions and all, but bring out to the surface this particular semantics of the program, but it is done as part of semantic analysis many times. So for example, here you can see that we have said initial plus rate star 60, and if the rate is a float, initial is a float, position is a float, then I need to convert 60 to real.